Can you guys hear me okay?
Yep.
Yay. All right. Thank you. I had some kind of weird problem with my audio. Let me just see if I'm on the screen here. Here we go. All right.
Hey, Dr. Kyle.
I've only got a tiny tool on my board, which is why I hate Zoom, but so we're talking about Newton's laws, and we summarized them last time. We sort of stated them a little more precisely last time. We said that the first law is I'll ask you these kind of questions, give you examples, and they're hard to do. For example, can someone tell me, so if I have my cup, right, here's my cup, sitting on the table. So let's identify some forces on it. So let's see if I can hear you guys. Somebody offer me a force that's acting on my cup that's sitting on the table.
Normal.
Say again?
Normal force.
The normal.
From the ground.
Yay. So gosh, I have no volume on this thing. It's such a, I don't know about that. All right. Well, hopefully we're not going to be zooming a lot. What is the source? What produces the normal force? All right. Chris is in class and he said the table. And so this is due to the table, right? So what's the equal and opposite force for the normal force?
Gravity.
Let's come back to that. So this is gravity is a force that's acting on the cup, right? Times G. And so if we look at the normal force, it's an upward force. Can you still see that? I know I'm right at like the edge, right? It's an upward force due to the table on the cup. So if I just blindly grab Newton's law, third law, what would the equal and opposite force be for this one? You can type it into the chat if you want. Everybody's quiet. I live for awkward silences. So if this is an upward force due to the cup on the table, then this has to be a downward force sorry, this is an upward force due to the table on the cup. This has to be a downward force due to the cup on the table, right? In other words, it's the same one where I said in class where I'm leaning against the wall, right? If I push down on the wall or in on the wall pushes out on me, right? And so if I know that the cup is pushing up on the table, which I know it is because otherwise gravity would pull it on through, then I know that the cup has to be pushing down on the table. Notice that equal and opposite forces are never on the same object, right? It's A on B and then B back on A. And so usually you can figure out what the equal and opposite force is if you look for the source of the force and the force that the object is on and just reverse them, right? And sometimes it's awkward. So for example, okay. So this is the normal force of force that's acting on the cup. The equal and opposite force is the force that's acting on the table. You identified another force, said the force of gravity on the cup. So what is the equal and opposite force for this one? Say again?
Is that just the cup pushing back against gravity?
Yes. So what is the source for the gravitational force that's being exerted on the cup?
The gravity times the mass of the cup.
Yeah, that's the value of the force. But what is the object that's producing that force? I'm not being super clear about my question, but what is the object that's producing the gravitational force on the cup? Right. There's an object that's exerting this gravity force on the cup. What's the object?
The Earth.
Yes. And so the force of gravity, and now I kind of have to say on the cup, right, has an equal and opposite force. If I write it this way, the force due to the Earth on the cup, this thing that I call the force of gravity, is equal to minus the force of the cup on the Earth. That is to say that the Earth is pulling down on the cup exactly as hard as the cup is pulling up on the Earth. They're pulling each other with equal and opposite forces. And it sounds comically silly, but it's just like the moth in the truck. It's exactly true, right? And if those were the only forces, that is, say, if I held my cup and just let it go, right? So that I'll use a marker because my cup has water in it. But when I let the marker go, in the time where it's in the air, if I neglect air resistance, it's being pulled down on equally hard as the Earth is being pulled up on. Right? And so the force of gravity due to the Earth on the cup is just the opposite of the force of gravity due to the cup on the Earth. They're equal and opposite forces. And notice if those are the only forces acting, I can say, look, the force due to the Earth on the cup didn't do a very good job of that. We already said that that's what that is. It's the mass of the cup times the acceleration of gravity, right? And so, and so the gravitational, the acceleration is g, right? That's the acceleration of the cup. It is not also g when you look at it the other way. The acceleration of gravity, g, 10 meters per second squared, is a property of the Earth, right? And we'll break this down later on and show why it looks like, why it is what it is. But the cup doesn't have a g that's the same thing as this g. The Earth just experiences that force and has a certain mass and gets an acceleration via Newton's second law. And so we can say the acceleration of the Earth is the same force, but now it's divided by the mass of the Earth, which in kilograms is a 6 with 24 zeros after it. So the Earth doesn't really move at all. These equal and opposite forces act on different objects. So the normal force due to the cup on the table has an equal and opposite, sorry, due to the table on the cup has an equal and opposite force that's a downward force due to the cup on the table. Similarly, the Earth pulling down on the cup has an equal and opposite force of the cup pulling up on the Earth. They're acting on different objects, right? So you should never see an equal and opposite force acting on the same object. All right, those are a few applications of Newton's, Newton's second law on a simple object. Just give me a second. Forces are vectors and obey vector math. And so, so all the stuff we did in chapter 1 and I think part of 2, all the preliminary stuff we were doing was applies to forces. And so I can say, I can just make one up and say, two dogs are attached to poles by leashes. And so I'll just, this is a top view, right? And so I'll say, dog 1 is pulling with a force of 100 newtons in the x direction, and dog 2 is pulling with a force of 200 newtons. I'm going to try to make that a little more scaly, so it looks twice as big at an angle of let's pick a number. How about 45 degrees? So what's the net force on the pole, magnitude and direction? We're basically being asked to add these two vectors, right? And the way we add vectors, we talked about this back when we were doing vectors, is we break them into components and then add the components and then rebuild the vector. And so we would say, look, we can call this F2, right? And if I draw a straight line down here, this is F2x, and this is F2y. And if that angle is 45 degrees, then I can say, look, F2y is equal to F2 sine 45 degrees. And F2x is equal to F2 cosine 45 degrees. And I don't know what that is. So sine 45 degrees is 0.707 or something like that. And so if I multiply that by 2, it's about 141, I think, newtons. Yeah. And same thing with this guy. 141 newtons. And so then F1x is just 100 newtons because it points all along the x direction, and F2x is equal to 0 newtons because it has no component along the F1y, 1y, it has no component along the y direction. And so now I can say, look, F total along the x direction is just the sum of the forces in the x direction, which is F1x plus F2x, which is 100 newtons plus 141 newtons, which is 241 newtons. This is the sum of the forces in the x direction. Similarly, I can say the sum of the forces in the y direction is F1y plus F2y, which is just 0 plus 141 newtons, which is just 141 newtons. Not doing a very good job of that. And so now I have my total force in the x direction and I have my total force in the y direction. And so when I add those two up, I get the sum of the two vectors. I can draw that graphically by saying, look, I'm going to redraw F1 plus F2. If I do this vector wise, I take F2 and add it to the tip of F1 like that. And then this is F1 plus F2. Right. And so basically what I've done is I put F1y here and F2y and F2y here. And so, F2x here, I get F1x plus F2x in the x direction and F2y in the y direction. Kind of made a mess up, so I'm going to redraw this. So this is my F1. That was my F2. And then I just redrew F2 over here like that. And that is F1 plus F2. This is back to my 45 degrees. This is 200 newtons. This is 100 newtons. And so this distance here is F2x, which is 141 newtons. And this is F2y, which is 141 newtons. And so my F total So the magnitude of my total force is the square root of 241 newtons. squared plus 141 newtons squared. 576 plus 280 maybe? Yeah. Thank you. So the magnitude of my total force is that, and the direction, right? I can say theta is equal to tan inverse of right. So this is the angle that I'm interested in, right? That was my 45 degrees there. And now this is the angle I'm interested in. It's a smaller angle because I've got more distance in the x direction. This is my theta. And so I can say tan theta, if I want, is equal to f tot y over f tot x is 141 newtons or 241 newtons. If I was going to take a wild stab at that, I'd say 30 degrees. What did you get? Did you calculate 30 degrees? So now I have I can treat my forces as vectors and break them down. And the what we've done here, really breaking these down into x and y components, is the essence and applying Newton's laws is the essence of solving problems. Most of the time, we'll be doing this sort of thing. We'll be saying, look, we'll write Newton's second law this way. The sum of the forces in the x direction equals the mass times the acceleration in the x direction. The sum of the forces in the y direction equals mass times the acceleration in the y direction. This is the same thing we were doing for kinematics, where we said, look, we're just going to separate out all our x stuff, and we're going to separate out all our y stuff. These forces in the y direction are only affecting y motion, and so I don't have to worry about them for x motion. The forces in the x direction are only affecting x motion and not affecting y motion. And so I only have to worry about them this way. And so we will maybe for the rest of time, we'll be thinking of Newton's second law really this way, instead of just as a general statement about the sum of the forces equal to mass times the acceleration. If you're just working in one dimension, of course, there's no difference really, right? But if you're doing more than one dimension, 2 or 3 dimensions, this is the way to do it. All right, give me a second. So we're going to start talking about free body diagrams. A free body diagram is a way of sort of isolating what's interesting to you about the problem in a way that it's easy to apply physics to it. And so, so let me just. I'm just going to work an example here. That's what I'm going to do. So here's the idea for a free body diagram. So in this problem, it's pretty easy to tell what object we're talking about, right? Ooh, did I come off the screen? Really? How about that? Just a little bit. Actually, that's probably fine. So the first thing you do when you're drawing a free body diagram is you represent the object by a dot. And so instead of drawing a rocket, I could draw a rocket over here, right? It's always good to just draw a basic picture. These often pictures help you identify forces. And so there's my rocket. Here's the ground. Right, and maybe there's an astronaut inside looking out a window smiling, something like that, right? And so, so there's my rocket. But when I start to draw a free body diagram, when I want to break this problem down, I represent the object by a dot. So where am I going to do that? My room over here. I'm going to do it over here. I think that's right. So here's my object, and this is my rocket. So here's my free body diagram. So step 2 is draw the forces acting on the object as arrows leaving the dot, right? And so let's start with this picture and let's just identify, somebody tell me a force that's acting on the object. What's a force that's acting on my rocket? Any force.
Gravity.
Yeah, thank you, gravity. So force of gravity is mass of the rocket times g. What's another one?
The opposite, the rocket working against gravity.
Yeah, so the thrust, right? It's the engines, and so I'm going to call that Ft, right? Basically, I'm burning fuel in the back of my rocket, and my rocket is pushing the fuel out of the bottom, and the fuel is pushing up on my rocket with an equal and opposite force. So we're going to talk about it that way, but that's exactly what's happening. And so I get a thrust force here and a gravity force here. And for this case, that's really it. Now I could actually talk about wind resistance also, which is really important, but we're gonna neglect that for now, right? And say, look, I have the weight acting downward, and I have a thrust force acting upward, Ft. Step 3, identify the direction of the acceleration. So what's the direction of the acceleration in this one?
Up.
Where's the rocket going to go?
It's going to go up into.
Yay, up, right? And so I do this. Notice I didn't put the acceleration as on the dot. I put it adjacent to it because acceleration is not a force, right? All the forces go on the dot. The forces are the thing that act on the object. The acceleration is the result of the force. And so this is really important. Keep that in mind when you're working problems. Acceleration is not a force. It's what happens at the end of the day. We end up with our equations look like this. The sum of the forces equal to mass times the acceleration. Often we're looking for this. right? And so we say the acceleration is equal to the sum of the forces divided by the mass. We're using this tool as a way to identify all of the forces that are acting on the object and perhaps determine the acceleration. Here they give it to us. But in principle, at any rate, we want to keep these things separate. The forces act on the dot, the acceleration is adjacent to it. Step 4 is identify a coordinate system that has the acceleration acting on some axis. And so you want to pick a coordinate system. You know, the obvious coordinate system we pick for most problems is this one, y and x. There'll be times where we won't want to do that, and it will be because the acceleration isn't along one of those axes. But before you pick a coordinate system for your problem, identify the direction of the acceleration, and then choose a coordinate system so that the acceleration is along one of those axes. We could have picked a coordinate system with y to the left and x down if we wanted to. That would still be fine for this, because that would put y to the left and x up, because that would put the acceleration along with plus x. You can pick any coordinate system so that a was along plus or minus x or plus or minus y, but since this is the one we use all the time, we just use this if a is vertical or horizontal. The reason for doing this, I'm going to have to erase this, so I'm going to have to come back to it. When we're solving problems, particularly in 2 dimensions, these are our tools. If we pick the acceleration along either the x or the y, the other one is 0. And then all of the acceleration is along one axis, and we don't have to have sines and cosines for our acceleration, which is often the thing we're after. And so, of course, it doesn't matter what coordinate system you use to solve a problem. The velocity of the rocket or whatever about the rocket is independent of which coordinate system you pick to study it. But there are easier ways and harder ways to do it. And it's almost always easier to put the acceleration along an axis. And so that's why we have a step like that, right? Step 5 is determine the x and y components of force vectors. So I could have had a force that was going off in this direction. It could have happened, right? And then I would have to go back to here and say, all right, well, this is an fx, and this has an fy. And of course, this has to happen after this happened, because I have to have a coordinate system before I can decide what my x and y components are. And so we want to make sure we determine these x and y components, because once again, our tools for solving, our algebraic tools for solving are these two. And just like I can't use a velocity for projectile that's off in some random direction and plug it into my kinematic equations, which are in x and y, I can't have a force going off in some direction and plug it into these force equations, these dynamics equations that are in x and y. So in our case, just make sure I'm not missing a step. It's close enough. So the whole point of all of this work is to feed into those equations, right? All this work, we do all this breakdown and stuff so that we can answer, so that we can get X components and Y components that plug into our acceleration equations, our Newton's second law equations. And I cannot emphasize that enough. These are the algebraic tools you use to solve Newton's law problems. And there's a lot of math that has to happen here, but if you do this part right, the problem is solved. You've just got an algebra problem to solve, which may or may not be hard, but if you don't get this part right, you're doomed over here. And so getting this free body diagram right and being thorough and careful about this procedure is paramount. It's really important. It's the same way with, for me, those kinematic problems that we solve. The challenge there in kinematics, projectile motion and so forth, is identifying what all those variables represent. Y and Y naught and X naught, V naught Y and V naught X and VY and VX and A. All of those, if you sit down with the problem and lay it out at the beginning and know what all those things represent, then you're just solving a little math problem at the end of the day, right? You've just got a set of equations that you have to solve. And you guys are all good at that at this point. And so being able to read the problem and identify what the projectile parameters are, what all those variables are, or in this case, being able to lay out the essence of the problem in terms of one object of interest and what the forces are acting on it, and then breaking all those forces down as necessary is for me, that's where the problem solving happens. And then you're just doing some algebra at the end of it, which may or may not be hard, but it's just an algebra problem. Okay, so we're back to the rocket. So this is the rocket, right? And so what this one really says is the sum of the forces in the y direction equals ma sub y, right? I don't have anything in the x direction in this problem, so I can just put a line through that one. And then I can say, well, this says that the force due to the thrust minus the force of gravity is equal to the mass of the rocket times the acceleration of the rocket. Or the acceleration of the rocket is the difference between the thrust force and the weight divided by the mass of the rocket, which is sort of what we expected. Let me do a little more on this here for a second. I'm going to add to that problem. So I'm going to erase this. I don't know why he has a spacesuit on already, but whatever. So somebody tell me, what are the forces acting on the astronaut? Give me one. What's a force acting on the astronaut?
Gravity.
Yeah, gravity. All right, so gravity is pulling down on the astronaut. I can call that mass of the astronaut times g or something like that, right? Now, what's pushing up on the astronaut?
Would it still be normal force?
It is a normal force, right? Why isn't it the thrust? What's the thrust acting on?
The rocket.
Yes, right? So I don't know how the inside of rockets work. I have some idea, but if you go to Stafford Museum, they have these giant rocket engines, right? And you're spraying gas down in here somehow, right? And it's burning. And we talked about this a little bit last time for our little rockets, this stuff is ignited and the rocket gets thrust because this chemical reaction is happening inside here. And this stuff is literally pushing on the rocket, right? And that's fine. That's making the rocket go up. We don't care about that in terms of this question, because in terms of this question, we're asking what's acting on the astronaut. And what's acting on the astronaut is the Earth pulling down on them and the floor pushing up on it. We may not know why the floor is pushing up on it. This could be a giant a monster that's throwing the rocket upward with its paw, right? All we know is that the floor is suddenly rising on the astronaut and pushing him upward. And so instead of what I had before, I have these two forces that are acting on him. And so I can say, if I wanted to draw a free body diagram, I would have a very similar free body diagram with forces of different names, right? By the way, how is his acceleration related to the acceleration of the rocket? Is the astronaut moving any differently than the rocket is moving?
Equal.
They're the same, right? Hopefully, for the sake of the astronaut, hopefully he's still inside the rocket the whole time, right? It'd probably be bad if he wasn't, or she, right? And so the astronaut is moving with the exact same acceleration as the rocket. Not that it's necessarily relevant to this problem, but it's important to know that if these two guys, if we're asking some questions about the rocket and the astronaut, that we can recognize that those two accelerations are the same. And so once again, I can pick a very similar coordinate system for this one. And then I can say, you know, the sum of the forces in the x direction equals ma sub x, and I don't have any of those, and so I can just toss that out. And I can say the sum of the forces in the y direction equals ma sub y, and that's just mass times the acceleration, right? The y direction acceleration is just a. And so in this case, it's the normal force minus the force of gravity equals the mass. And this, not the spaceship, but the astronaut is the mass that we're talking about now. And the force of gravity is the force of gravity on the astronaut. And so I can say the normal force is equal to the mass of the astronaut times g plus the mass of the astronaut times whatever acceleration it has. All right, that's a good stopping point. I'll do some more. We'll sort of work our way into some more significant examples. We'll be identifying new types of forces. Thanks for your patience with me today, guys. I appreciate it. And hopefully I will see you in class tomorrow. If not, I'm probably just going to do this again and hopefully won't have to do it a lot. If you have any questions, I'll hang around here for a minute. Otherwise, I will disconnect all of you and see you tomorrow. Say again? I don't think it's going to snow this evening.